Today we're going to do some examples on mathematical induction. So the first thing that you want to notice is that there's 3 steps to follow for mathematical induction. The first one is the anchor step, prove that the statement is true for its first value. The second is inductive hypothesis, assume the statement is true. And the third step is the actual inductive step, prove the statement is true for the next iteration. I'm going to be referring to these steps throughout the video today. We'll do a couple of pretty straightforward examples that I've pre-written, and then we'll go through a longer example together. First, let's prove that 8 to the power of n is greater than or equal to 8 times n for any n greater than or equal to 1. The first step is straightforward, of course. Just plug in n equals 1. And you'll find that 8 to the power of 1 is greater than or equal to 8 times 1. The second step is literally to just assume that the statement is true. And the third step is the real trick. Prove 8 to the n greater than or equal to 8 times n for the next iteration, which can be written in this form. 8 to the power of n plus 1 greater than or equal to 8 times n plus 1. For example, if n was 1 last time, then it must be 2 next time, right? So that's why we put a plus 1. Because we want it in this form, this is a couple ways to get there. We could just plug it like this, that's acceptable. But it wouldn't be the right way to solve this question, in my opinion. What we should do first is actually multiply both sides by 8, so that we can get the left-hand side to look like what we want it to, 8 to the power of n plus 1. And then we're going to just manipulate the right-hand side until we get what we want. So 8 times 8 is 64, and 8 to the power of n plus 1 is greater than or equal to 64n. Great! We can also split this 64 up into 2 terms, 8 to the n plus 56 to the n. This is all true. Notice how these equality signs haven't changed. We're going to apply a little fudging of the numbers here. 8 to the power of n plus 1 is greater than 8 to the n plus 56. Would you agree? Of course, because this term, 56n, must always be greater than 56. Right? If it's greater in that way, then we can also say that 56 is greater than 8. See how we're kind of messing around with everything here. But technically, we haven't broken any rules. The equality still exists. So that 8 to the n plus 8 can be simplified into 8 to the times n plus 1, which is what we want. That's your answer. That's how to prove this question. It's a little bit silly here, how you transition the numbers from here to here to here. But because we didn't actually break any of the rules, it technically works. The next question is a little bit longer. Prove that 3 is divisible into 4n plus 2. So this can also be written as prove 3 is a factor of 4n plus 2 for any n greater than or equal to 1. I just wrote it in this way because it's a little bit easier for me. This means is that you can divide the number on the right-hand side perfectly. In the first step, we'll see that if you put n equals 1, you'll get 6 here, and 3 divides into 6 perfectly twice. The second step, of course, is just assume the statement is true. And the third step is to prove that the statement is true for the next iteration. So we're going to take this equation, we're going to make it look like this. So let's start. We can just kind of take this as it is and put it here. We have to prove that this iteration is divisible into 3. We're going to break up this this exponent into 2 products, 4 to the n and 4 to the 1 plus 2, which is acceptable. And then we're going to do a sneaky little thing. We're going to actually break apart 4 to the power of 1 into 3 plus 1 times 4 to the power of n. We're going to just expand the terms here so we can get 3 terms. And at this point, we can basically just stop because you realize that this term, 3 times 4 to the n, will always be divisible by 3 because, of course, there's like a 3 in front of it. So at the very least, the 3's will cancel out. This second and third term here is actually what we had in the beginning of the question, which we can apply. We know that this is always true because we've already assumed it was true in step 2. And you just proved that the statement is divisible by 3. Good job. So this step equation is a bit more involved. I'm just going to do it together. We're going to prove that 1 plus 4 plus 7 plus blah blah blah, 3n minus 2 is equal to n times 3n minus 1 over 2. In the third step, we're going to apply that next iteration as I was talking about. But there's a special thing that we have to do here. Notice that the n term stays the same in 3n minus 2. We're actually adding another term on the left-hand side. It's because the first little bit here in blue is n equals 1, and then the next little bit in blue is n equals 2. But the right-hand side, we will replace all the n's by n plus 1, if that makes sense. I hope it does. Okay, moving on. The first things that we need to do is realize that the n equals 1 blue portion that I've kind of highlighted here is actually given to us in the beginning. It's n multiplied by 3n minus 1 over 2. And the next term can be simplified, or I guess expanded into 3n plus 3 minus 2. I'm just going to drag the right-hand side as RHS so I don't have to keep rewriting it. Basically, we want the left-hand side to look like the right-hand side at the end. So what are we going to do? Well, you should notice that the form of the first term is nice. We want to keep it like that because the right-hand side has a division over 2. But the second term on our left-hand side is not as nice. Let's make it look the same as the right-hand side by first simplifying and then multiplying the top and bottom by 2. When you multiply the top by 2 and the bottom by 2, it's like you never multiplied it at all, right? Now, we're going to expand the two terms together, which means that you're going to have to expand the first term, 3n squared minus n plus 6n plus 2 over 2 equals the right-hand side. Now, what you want to do here is to just use the quadratic formula. If you're not familiar with it, probably look that up. So I've applied the quadratic formula here, as you can see, my little doodle. And the left-hand side is factorized. So the last thing that we really need to do is drag that right-hand side down and prove that the two terms are indeed equivalent, which I will do now. N plus 1 multiplied by 3 times n plus 1 minus 1 over 2. The terms are equivalent. You can expand either one. Prove it to yourself. Well, thanks for watching my video. Give a like if that helped you out.